Hello everyone. Today we're gonna see some parameters related with the LM741, which is an operational amplifier we use in the construction of electronic circuits. Some general aspects are shown in this image. It consists of two inputs inverting and non-inverting according with the negative and positive signs, an output and a positive and negative supply commonly connected with a dual source. The pin connection of the physical LM741 given by the datasheet is the one shared in the screen. This parameter, called offset, is a deviation from the ideal output voltage value. In the physical circuit, the output value will always tend to vary a few millivolts compared with the calculated value. In the case of the LM741 amplifier, the offset value is typically 1 mV and maximum 5 mV. In the simulation, we can see it by measuring the output voltage with a multimeter when this input is connected to the ground. We can see it is the same as the typical value from the datasheet, 1 mV. This is an important parameter because if the amplification is too high, the offset could drastically change the output voltage. That's why we should always keep low amplification and take into account the offset value for each amplifier. For example, in this circuit right here, the calculated value is 10 volts, but with the offset the voltage is a little bit higher, as you can see. The supply range refers to the range in which the supply sources will make the amplifier work. The LM741 must have a supply of between 20 volts and 22 volts. You must take this value into account in order to make a correct amplification and the calculation of the output voltage. In the simulation, we can see that the circuit has a gain of 10, which makes the differential voltage of 1 volt and output voltage of 10 volts, as we can see right here. In a real circuit, if we increase the supply voltage above the 22 volts recommended by the datasheet, this one wouldn't work. In the simulated one, if we decrease the supply voltage above 10, the amplification won't work because the output voltage can be higher than the supply voltage. Let's see this. 9 and 9. We click start. It won't work. The amplification is not 10 volts. For the gain part, we must take into account that it will always be equal to resistance 2 over resistance 1. The value of the voltage will vary to the configuration of the LM741 amplifier. We will continue to see the three most important configurations that we have already shown in this video. Subtractor. Here the subtractor configuration is shown with its respective equation. The calculation shown here indicates that the output voltage must be 10 volts. Taking into account that the gaining value of the resistor is multiplied by the subtraction of the input voltage, 3 minus 2, hence is named subtractor. Here we can see in the simulation that the value coincides with the calculated one. Second, the non-inverter. Its circuit is shown in the screen with its respective equation. Here, the amplification value is added with 1 and multiplied with the only input voltage value. For this reason, the calculation of this voltage is 6, with 3 being the gaining value and 2 being the input voltage. This matches the simulation. Finally, we have the non-inverter. Those characteristic is to have a negative output voltage value as can be seen in the equation. This is multiplied with the input voltage. As we can see in the simulation, the tree of the input voltage is multiplied with the tree of the amplification. Leaving together with the minus of the equation, the result is minus 9, which coincides with the simulation value.
Hello, now I will explain what is CMRR. The CMRR stands for Common Mode Reaction Radio, which refers to the capacity of an amplifier to reject the interference generation in the signal changing in the inputs of a different amplifier. In theory, the common mode should be zero, but in actual electronic circuits, they will always exist. In the case of LM741, the CMRR is typical 95 decibels and minimum is 80 decibels. Calculate the CMRR, you must first calculate the AMC. To calculate the common mode gain, the differential input must be made equal to 0. For example, making the inputs equal to 1 volt and then the difference is made it equals 0. So that what they get in out in the simulation is the common mode gain, usually a very small value in millivolts. On the other hand, the differential gain must also be calculated. You can make the differential input equal to 1. For example, placing 0.5 in the non-inverting and placing minus 0.5 in the inverting. So that when the difference is made between 1 volt. So then we get in out in the simulation is the differential gain, which depends of the configuration and the resource gives the value. These two steps are used to calculate the CMRR for the equation differential gain over common mode gain. This value is normally given in device, so the equation is used 20 base 10 logarithm of differential gain over common mode gain again. The PSRR is a concept similar to the previous one, but in this case it stands for power supply radiation ratio and is related to the interference generated by the power supplies connected to the amplifier, which can be represented by placing a sinusoidal saucer on the power supplies, positive and negative, with to find the gain taking into account the power supply, either positive or negative. In the case of the LM741, the PSRR value is typical 19.6 decibels and minimum 86 decibels. The PSRR of the positive feed corresponds to the differential gain over the gain of the positive feed, and the PSRR of the negative feed is the differential gain over the gain of the negative feed. Continuing, I will explain two exit excursion range. Output voltage swing refers to how closing the output of the op-amp approaches the range of the supply voltage. For example, if in an inverting configuration the supply voltage is 10 volts, in a non-inverting and in inverting is 8 volts. The ideal output should be minus 20 volts. However, in the maximum positive and maximum negative supply voltage is 15 volts. The output voltage will be slightly lower. This can be seen in the datasheet where it says that the output variation can be at least about 12 volts or as a trend it can be about 14 volts. On the other hand, the input exclusion range is the voltage range that an amplifier must receive to function correctly. According to the datasheet for the LM741, it should have be minimum of around 12 volts and a maximum at around 30 volts to work properly. As see for the example, it is exceeds a voltage higher than 13 volts, the amplifier might be burned or damaged, and if the value is lower than 12 volts, it may not work. The next parameter is a maximum output current, which indicates the maximum current that can enter the amplifier on the output side than the current that is generated by the voltage to pass through the resistor connected to it. For example, in this circuit, it is calculated that the current passing through the resistors is equal to 1 milliampere. Since the maximum output current value in the LM741 according to the datasheet is 22 milliamps. If the amplifier did not have the ability to maintain this maximum current value, it simply will not work. One way to know since this value is to use the circuit resistance in kiloohms. And finally, this is the operating temperature parameter, because a semiconductor junction, that is transistors, is present inside the amplifier. Its behavior can vary with temperature, there where the operating temperature determines in which range the amplifier works optimally without superficial damage. The operating temperature of the LM741 is a minimum of minus 15 grades to a maximum of 125 grades Celsius. Although this depends on the type of LM741, as it can vary if it is R, A, or C.
Finally, last but not least, we have the power consumption. The power consumption is the amount of electrical energy that the op-amp consumes from the power supply while active. The supply current is the current consumed by the operational amplifier in an inactive state. The power consumption given by the datasheet of the LM741 is typically 80 milliwatts. This is an average value between the minimum and maximum power consumption. The way to prove this is very simple. You just have to make a buffer. This configuration right here is called buffer. And measure the current that goes through the amplifier, and it is given by the supply sources. This one right here, that it is 20 and 20. And 20 plus 20 is 40. That is the one that we're going to use in the formula. Then we can see that the current is 1.83 milliamperes, as you can see right here. Then we apply this formula right here to calculate the power consumption. you can see that the power is equal to the current times the voltage. Then we multiply 1.83 milliampere times uh, 40 volts, that is the one from the supply sources. And we can see that the value is 73 milliwatts, which is close to the typical value of the datasheet. Well, that would be all for today. Please consider to like and subscribe. Thanks for watching.